is the classification, which is first generation, how to get dropping fuel. Challenges. Getting technology is one component of turning into a business. You have a lot of other things, cost, finance, policy, who will fund it initially, who believes in it, go for loan, will they buy your idea or not. Community participation, lack of awareness, lack of technical expertise, logistics, all these issues comes up when we design as a product. There are tons of, numerous environmental benefits, economic and social benefits. There are more. I'll skip to case studies and then I'm coming to my topic. But some examples, National Bioenergy Program, India has it. Alright? Then Waste to Energy Program, they have it. They provide financial assistance, biogas program, National Green Hydrogen Mission. These are the funding major Indian waste to energy products. NTPC is a lot of work doing. I've seen IOCL doing, HPLC doing, HPCL doing. There are other plants, bioinformation plant, IOCL is doing ethanol project. CO2 can be converted to methanol. Then private sector, I've seen Reliance very actively doing for last 2 decades. Definitely they have a lot of focus on LNG to fuel, dropping fuel. Tata Steel is doing waste valorization. Adani Group started bio-CNG. International collaboration. There are many Indo-EU projects, Indo-UK project, Indo-US clean energy project, Indo-Japan projects going on. So this collaboration brings new ideas and is kind of takes you out of comfort zone. We are working something, you are working something, there is a crossover, and that helps solving a lot of things. So challenges, future map, it's okay. Future trends is okay. Now I come to here. So if we are given a land and asked to grow corn, and we will say this corn is bioenergy crop. We are growing this corn or whatever grass or something just for bioenergy. How much ethanol can be made or how much biofuel can be made? What would be the issue? That's the first question comes. Alright? That comes to efficiency. So let's say corn. If you are talking corn has 60 to 70% or 75% of the starch. Only a starch will be given. The kernel or protein part of it, corn oil will not give you this. Alright? So you have to have a biorefinery approach. What other products can be made? Okay? So DDGS and distillate grain and other things you can do. There are high protein content. What will be the proteins? Wheat, barley, sorghum, oat, rice, these are all first generation. And it depends how much ethanol yield you see that. You should be able to calculate yourself by just writing that formula, glucose to ethanol fermentation, how much you make. Glucose to ethanol fermentation, you know, C6H12O6, you get C2H5OH plus CO2. So this many kg will be this much ethanol. Now you put efficiency factor, then this much glucose is needed. Once you know how much glucose is needed, you calculate back how much starch was needed. Once you know starch was needed, you know how much starch in corn, so you know how much corn was needed. Now you know productivity of corn per acre, how much corn you can produce, so you know how big land is needed to set up a biorefinery. So in fact this table you can fill yourself, and that's how you design a plant. And once you know I need 100-acre land, now you go to techno-economic. What would be the transportation cost for such a big hauling area? So feedstock cost and other things. So let's go through one example. A starch can be represented as C6H10O5N. And a starch is polymer of glucose in hydroglucose. So you see C6H10O5. It will undergo through hydrolysis process. That means you will add water, H2O. So that H2O, 2H2 will come here, so this will become 12 and this O5 will become 6. And then we will start opening chain. So anhydrous glucose, add water and become a starch to this. So we have the degree of polymerization because the starch again can be 1000 or 10,000 degrees. It's a long chain. What will be the theoretical maximum yield of glucose and ethanol from 1000 kg of a starch? If 100% conversion is assumed, that is ideal. You don't get 100%, but just to simplify. During a start to glucose by hydrolysis, glucose to ethanol by a fermentation process. So there are two steps in making ethanol. The starch needs to change into glucose and glucose to be fermented to this. We should be able to estimate, calculate and tell the policy method that we need this much land, this much corn productivity, this area. This is corn, it can be sugarcane also. Alright, it can be any other starch source or sugar source. So a starch molecular weight what would be? C6H10O5. C6H10O5, let's forget N right now. We don't know N. Glucose 180, we just remember. Ethanol 46, we remember, but we can calculate. Okay. Now what is hydrolysis reaction? You add water, so you need n number of waters, it will become n number of glucose. So now this is 162 n because it is missing water again. So you can do math, 162 only. And then it makes 180. So if you have a starch, you will get glucose 1.1 times. If you have a 1000 kg of a starch, you will get 1100 of glucose. From material balance, you know that in plus out should be same, in or out should be same. But here it is not same, you are getting more because you are adding water. So when you plus water, it is same. Yes, water is increasing the value. And then we come to fermentation. So you got C6H12O6. Fermentation gives you 2 moles of ethanol per mole of glucose. So now you can go back, calculate, and this is roughly half, 51%. We see that. So 51% will get. So 1100 kg of glucose. I'm rounding 1100 kg convert to 567 kg of ethanol. Okay. Assumption is 100% efficiency. It may be 90% because many things, fermentation conditions and viscosity and other things matters. Alright, so now we are able to calculate 1000 kg of a starch will give you that much ethanol. Let's go back. Corn has 72% starch. Now you can go back and say how much corn you need. Right? Of that. Once you know corn, even farmers will take per acre how much corn you can do. Alright? So now you know how much land you need, how many rotation you will do, how big area and what size of corn and ethanol you find you can put. So once you give all these numbers, then there is a techno-economic guy who will be doing all plugging these numbers, will close it and we see what materials coming in, how cost. So they will say it's economical or not economical. So that's how we do. So it starts from very basic, we'll say. It can be more complex, but this is how it's calculated. So US corn, they are sold in bushel. Bushel is, they are more common there in pounds, not kg. So one bushel is 56 pounds or something with 15% moisture. Any time you are dealing with organic material, waste or corn and whatever, always keep an eye on moisture. Because you are paying for corn, not for moisture 15%. So you are looking for moisture free, how much material you are getting, but it's not moisture free, whatever will come to get. So price will be adjusted accordingly. If you have 30% moisture, then price will change. So per bushel with 56 pound with 15% moisture yield. Same math we have done. Okay. you can come out with this, which is handy for farmers. Now they don't have to do those math. So per bushel you will get about 2.8 gallons are common, not liters there. So 2.8 gallons. Then feed you will get proteins and gluten meal. Corn oil you will get, corn has oil. So you can have ethanol biorefinery and all, you can get all these things. My point is how to estimate. If you are helping an industry as a process engineer or biology side or whatever, how much you can produce, they are looking at you. So let's come to here, the lignocellulosic biomass which I started, and this is what I am saying, that this is the future. So a starch is not the future. It will go, but you cannot build multiple plants on a starch. Vegetable oil, sugarcane juice, no. So all these materials, what you see is foodie. This is food, alright? This is more fibrous, sugarcane. This is more grassy, alright? Here we will find more silica, inorganic material. In food you won't find much silica because the way it grows. Yesterday I started the discussion, I am coming back because it is very important to understand what it is. So you take a log, a chip or something and you want to put a microscope and simplify how it looks. Cellulose is a straight chain of anhydroglucose, C6H10O5N. And how it's different from a starch? Remember, I gave you two lines, and one is a starch, one is this, one is alpha, another is beta, 1,2-glycosidiol. Beta makes you fiber, very strong. Alpha makes you easy to digest. And that goes in our intake also. We say carb versus fiber. So truth comes from here, knowledge comes from here. Okay? So this is your brick. Hemicellulose is also glucose as sugar. But that is not single sugar. If you have cellulose, you can hydrolyze, you will get only glucose or oligomer or dimer or something like that, but they are only on glucose. If you hydrolyze hemicellulose, they are branched, okay? And they are a mixture of sugar. How many sugars you know? Anyone? Besides glucose, what else you know in sugar? Lactose, mannose, sucrose, fructose, xylose, arabinose. These are all sugar. And when you hydrolyze this, you will get mixture of this. And plus organic acids, acetic acids, they are branched here. So now you see the difference. If you have a starch, you can hydrolyze, you get glucose, nice clean fermentation, ethanol. No worry. If you hydrolyze this one, you are going to get mixture of sugar. Now we design baker yeast. It likes glucose fermentation and takes it. Will baker yeast will take this mixture of sugar. It won't take. It will be very slow, inefficient. Alright? So now the challenge comes. We are trying to digest something like a woody or grassy material using biochemistry, biological pathway. Now we have to look at right enzyme mixture, cocktail of enzyme, which will do effective for multiple sugars. So a starch or potato easy to make ethanol. This one comes challenge. Not only that, the outer layer is lignin, and lignin is aromatic. Lignin is called young coal, brown coal. Basically, coal when it is formed, basically lignin is the starting point. So can you ferment coal? Can you biodegrade coal? No, you leave it outside, it will remain coal, alright? And that's very close to that, not exactly that, but a young coal. So now you see the challenge. You have to do very clean separation to get cellulose. like paper industry does, they are worried about these fibers. They don't do hydrolysis, they want to protect it as it is, they don't want to cut it. But for ethanol, we want to cut it also, release enzymes go and do that. And we want to stay away from lignin because that is going to reduce your efficiency. It won't be biodegradable, means it won't be digestible, plus it will be thick, it's aromatic. So ask a company and ask for business, they will say, I'll take sugarcane juice for ethanol making. Bagasse will be costly. Commercially it's costly. That's where we are looking at you. What kind of enzyme, what kind of process condition, how you will hold this fiber so that enzymes work efficiently. Even if you have a right enzyme for this, you have to cross this boundary. Alright? You have to do some pulping or something so that lignin goes out. Then only enzyme will work. So this is the challenge. And depending on feedstock, whether it's wood or whether it's a grass, this value changes. So these two together about 65 to 70% are carbohydrates, carbs. This is aromatic lignin. A little bit of other things are inorganics, extractive, those kind of things. And we are looking biochemically to do this fermentation biologically. So that's the challenge, finding a right enzyme, right microorganisms, and then we go to fermentation. So look other way, if we go thermochemically, what we have? We will not recognize it is hemicellulose and near lignin. We will break down everything as a carbon, hydrogen, oxygen. Use heat and change it to gas and something like that. Pyrolysis. The yield will matter, but you can do those things. Alright, it's not very sensitive to what you have. So should we go thermochemical route? Should we go biochemical route? It depends what feedstock you want, what efficiency you want. That's where we decide. So little more on this. I already talked. So hemicellulose, if you want to represent, we call it xylan. Okay, xylan, and carbs are called glucan also. Glucan. So cellulose, some people call it glucan because glucan hydrolyzed to glucose, we call it glucan. Xylan hydrolyzed to xylose, we call it. It's a mixture of sugar, but xylose is most, we call it xylan. Okay, this fiber and microfibrils and their dimension are 10 to 30 nanometer. This is very simplified arrangement, brick mortar arrangement, but it's more complex than that. Interface is called lignin carbohydrate bonds. They are joined together. It's not such that you chip it and it will go up. So 2 units of hypothase is called cellobiose. Some people call cellulose is a multiple unit of cellobiose. That's why. They are the purest form of glucose and cellulose. If you got 3 and you get cellulose, you have to do something, pulping and releasing. The purest form of cellulose is water, white water. Right? That's pure cellulose. That's pure cellulose, and how strong it is, you know. But there you can design enzyme to break it down because it's not contaminated with other things. Its degree of polymerization can go up to 7,000 to 14,000. Paper industry keeps an eye on that. The longer, the greater fiber or shorter fiber, what they want to make it. Okay. These units are cross-linked fiber, but intra-bond and inter-bonds are the hydrogen bonds are there. They are linked together. Why I am bringing those things? If you are looking at biochemically, what are the bond needs to be cut to release glucose? Hemicellulose, I already talked all these things. It's a mixture of sugar, pentose and hexose. Pentose is 5 carbon sugar, hexose is 6 carbon sugar, and then you have branching, you see COL seeding, that is organic acid coming out. So when you cut it off, digest using enzyme, you will get mixture of things. The good quantity, it's a softer, it's amorphous. So at low temperature it gets cellulose removed. 180, 200 degree hot water wash will take it out. But nothing will happen to cellulose in that condition. So you can fractionate. Now this cellulose has commercial use. Furan chemicals can be made from that. Okay. Furfural is a chemical made from cellulose. So that's how it does. You separate cellulose, lignin, and hydrolyze this, and you can get furan based compounds, and you change it to furfural. So that's a finished product and industrial product. The hemicellulose is not long like cellulose. It's a small chain, branch chain, mixture of sugar. There are many side groups. Lignin. So straight chain, nice cellulose fiber. Hemicellulose we do understand. Now you understand here what you see. This is lignin. This is lignin, this is the representation. What you see. When you saw cellulose, there was repeating units of glucose. Hemicellulose again repeating your different sugars. What you see repeating here? It's built on something, am I right? Repetitive units, a polymer. So now when you look at closely, you will find these two monomers. Lignin is built on that. And these are aromatic. Okay, that's immediately for many things. Lignin properties, molecular weight or degree of polymerization is not like cellulose. It's different bonds you will see, CC bond, COC bond. If you want to represent as a formula like cellulose or a starch, we represent C6H10O5 again. If you want to write lignin somewhere, this is the way to write C9H10O2 OCH3 with the repetitive units. Now you can do material balance because you need formula for those calculations. You can represent like that. And this is varies, so if you are looking thermochemically how much, so all these things while you are looking, they are renewable carbon, right? I'm going more deeper cellulose, hemicellulose, but as a bigger picture they are carbon, renewable carbon source. So you are looking at what percentage carbon you have. In lignin you will see 60% carbon, 59 to 60% carbon. Tell me what percent of carbon in glucose or cellulose? If you are given glucose, can you tell me what is the percentage of carbon in glucose? C6H12O6, 180, alright? C6, 72, 72 versus 180 is 40% carbon. Okay, that is your renewable carbon to any use. 40%. Cellulose little higher because oxygen is O5 not O6, so it is 44% in that range. Lignin, if you are looking at a just carbon, you can add 60%. So that's why you will see that ethanol refineries, bagasse, leftover material, they burn for heat. Right? Leftover after ethanol, they burn for heat, run for electricity. If you are burning sugar for heat, not much because it's less carbon. But here lignin will give you more energy because it has more carbon. So one of the easiest thing you do, burning in a refinery, get electricity, support the heat. That's how that model. But that model can be improved if you can take this leftover material like furfural or ethanol or another thing, then you have more value to heat. Alright. Liquid fuel have more value than solid fuel. And yesterday I talked why, because handle easy, contain, burning in coal, we have more energy. Bioproducts in market you will not realize, but there are many products which we are already using. They are commercial. glutamic acid, glutaric acid, glycerol. These are all furan-based chemicals. Phosphorus will be here, HMX will be here. So there are many chemicals is being made. Okay? It's not something is not used. We are looking for what more commodity things to be made. This is from Second World War. This bus is run by gasifier. Also, Germany. How much oil they have? Not much, right? They bought. How much food they have? A lot. During wartime, fuel is the main thing you want. War will stop you to have fuel. You cannot fly, you cannot move. So they came out with real cut of things. So they came out with why not use food for gasifier and run our transportation system. So that's where it started. Economic issues of bioenergy conversion. What is the cost of biomass? There are two kinds of feedstock. One, you are going or buying from farmers makes you fuel out of it, products. One, you are getting free and you are hauling to some location and making product out of it. The product which you are getting free, you are paying money for transportation, for water and other things. City cannot dispose, so you are coming as a contractor, will take it and make fuel. The other place you are buying grass or wood, make fuel out of it. And the cost because that's where economic comes, what feedstock you have. Okay? So project cost of biomass, projected cost of biomass versus heating value. This business energy is heating value. How much heating value you have, and based on that you will take price for it. Cost of energy derived, how much cost of biomass versus how much energy conversion you do, efficiency. So viability of any project is for following several items. Cost of electricity, how much electricity needs this process, how much return you will get. Go to a business anyone, what is IRR, investment, return on investment. If it is not attractive, they will not do it. Then you will not. So that's one thing. Net present value, benefit cost ratio, payback period, how soon I will get money back. Okay? Life cycle cost. So those are the things guides how the business or how to set it up. Okay, now let's continue with the property and characterization. We learned what it contains. I give you wood chip and now you will say it has fibers, cellulose, hemicellulose and lignin. Now I will ask you how much cellulose it has. Because that's important. Saying that it has cellulose is just give you some idea, it does not solve anything. Right? It has lignin, it gives you some idea. How much lignin you want to know? How much hemicellulose you want to know? If you are looking at the renewable carbon, how much carbon it is? How do you analyze? How will you put number to these facts? That comes to lab analysis, how we do that, how we characterize it. Okay? So if you look at, there is no single number. You bring corn, you bring sorghum, bagasse, hardwood, softwood, switchgrass. They are all variable numbers. So you can design a plant for bagasse, and then someone comes, why don't you take some woods in it? Then you have to tune the plant to match the uniform with the stock and do this. So things changes. Okay, so now there are two kinds of analysis. Your biochemical, you are looking at how much cellulose so that you can calculate how much ethanol will be. If you are a thermochemical, you are looking at how much carbon, how much oil it can produce. So let's go one by one. So for biochemical, cellulose and hemicellulose components are important because those will give you a food. So how do we analyze cellulose? Anyone? Have you done biomass analysis in your lab? Pardon? Then? Yeah. So, very basic method is where it has started. Lab analysis method does not lead to a commercial process. But that is designed just for labs. So don't worry about cost and all. You can be very aggressive, you do that. Someone comes over, I take lab process and expand by witnessing, don't worry. Okay? So what you do, a strong sulfuric acid, 72% to apply to that. Okay? You do dilute second stage 4% and then do 100 autoclave basically. 100. It releases cellulose to glucose and then you put in HPLC, high pressure liquid chromatography, and it will tell you under the area how much glucose you have. Now once you get glucose, you go back to how many cellulose was there based on that ratio. Okay, it's all mass balance. So lignin which residue measured by gravimetric, but cellulose you hydrolyze. Why use sulfuric acid? Hydrolyze cellulose. Okay, it's a very long chain. When you start hydrolysis, some may turn to glucose, some may still soluble but oligomer, dimer, trimer, and other things. So they are called oligomer up to 8 to 10 units. Second stage hydrolysis makes sure that you reach to this. So that's why 2 stages of sulfuric acid analysis application and autoclaving will give you glucose, run through this HPLC, under the curve, and all sugar mixes you can calculate that, and you will say this much cellulose we have. Okay, the leftover residue is mostly lignin, and once you measure leftover things, it's lignin, you can burn it, put in an oven and do the gravimetry. So mass lost from that, so I'm simplifying the complete method how to do that. So giving a bigger picture how it's analyzed. Thermogravimetry, you burn it, the white loss is lignin, leftover material is ash. So you started cellulose and hemicellulose gave you thick because of sulfuric acid hydrolysis. HPLC gave you amount of sugars. So how much cellulose and hemicellulose you calculated using this, and then leftover residue was mostly lignin, so you burn it and you get how much lignin was there and how much ash. This is how we analyze lignocellulosic material. Now once you know how much cellulose, then you know how much ethanol can be made, how much enzyme you need. So this is the bigger picture. Want to do in lab, go to these links. Okay, this is called NREL protocols, National Renewable Energy Laboratory. They came out with a method for biomass composition analysis. They have a step by step methods what you need, and just follow that and you will get it. Now come to thermochemical liquid design, pyrolysis and other things. What important? Temperature. You are subjected to temperature. So what is important? Weight loss, how it will happen. Alright, how much carbon will remain of the gas stage, how much will remain in solid, and those kind of things. Then so for that we do proximate and ultimate analysis. So proximate analysis and ultimate analysis knowledge base comes from coal industry. If you are talking to coal industry or thermal power plant, they are interested in knowing proximate analysis of coal. That way they will know how much fixed coal, how much gas, how much moisture, and how much fixed carbon has. So moisture plus volatiles plus fixed carbon plus mass is 100%. This is called thermogravimetry, TGA. Many labs will have TGA. So TGA, what it does, you load samples on a pan. The instrument heats at a given heating rate. You can decide 10 degree per minute or 20 degree per minute. You look at the protocol ASTM method how to do. And then what it does, time versus weight loss. And another side temperature also you can plot. It gives you this weight loss, initial weight loss around 100 to 150 degree, mostly because of moisture, right? Then you will see drop in weight, mostly because of carbohydrates. Volatiles and other things will go out. Then leaking takes time. It's a very complex mixture. So weight loss continues. Then you are left with fixed carbon. This is not going to gasify at that temperature. So at that time you supply air. This is done without air. Now once you get fixed carbon, you run air. So this fixed carbon will burn. The weight loss, then you can get how much fixed carbon was there, and then leftover material is ash. You don't have to remember. What you want to remember is this is what proximity is. How to do? You need TGA and you need to follow ASTM method with it. This method just upload, go step by step. Okay? So now look at this. Most of the lignocellulosic or organic waste, they will look like this. Volatiles more, fixed carbon less, ash and some moisture. Put coal next to it because the knowledge base comes from coal. Coal will have more fixed carbon, less volatiles. So volatile matters mostly, now you can see that fixed carbon, all these things go through. Now let's come to ultimate analysis. What is ultimate analysis? We are doing again, we need to do thermochemical process, gasification, pyrolysis. We need to know how much carbon is there. That's value we are paying for biomass, what we just taught. So ultimate analysis is elemental analysis. The name suggests ultimate means you broke down everything. We are talking at the carbon, hydrogen, nitrogen, oxygen, sulfur level. Okay? So again, these are ASTM methods you don't remember. I am trying to make you understand how it is done and why it is important. So carbon, hydrogen, nitrogen, sulfur and protein and ash, these are measured. Again, it comes from coal industry knowledge base applied to biomass. So all this together, moisture, ash plus all these elements, that's what the biomass has. These are the major elements, X 100%. That's the assumption. Now there is an instrument called elemental analyzer. Okay. Again, major companies supply elemental analysis module, and there are many versions of it. So you can use it. They apply temperature, burn biomass, and then they have detector. So if you combust biomass at high temperature, you will get CO2, right? The detector will sense CO2 and tell you back how much carbon was there, so CO2. Same with nitrous oxide, so they will tell you CHNOS values, percentage. Now you can put it that, that's how you will say ultimate analysis. Okay? If you put it like this is biomass, carbon 40%. Someday if someone in lab, if you are doing analysis and you getting 80% carbon, then that is wrong. If it's a raw biomass and nothing done, and you are getting 80-70%, it is wrong. Okay, so we should do analysis as one thing. If I bring something to your lab and say, give me analysis, first thing we'll ask, what do you expect? How much you expect? When I was BARC, BARC, we used to do a lot of uranium work. Okay. So we have some samples, we'll go to lab, analyze what percentage of uranium compound it has. The guy will ask, I was young at the time, new, so they will ask, how much you expect? Then I'm taken back, I'm bringing for analysis and you are asking me, how much is spent. Then I realized over the time that you need to have a calibration curve, you need to understand what the consumption data is only analyzed. You need to know the range, and that will give you. So you have, this is the range you are working on. Now this can be here, here, here. It cannot be here, right? Biomass. If you put coal next to it, what will you see? Coal will be here, this much carbon, 80-90% coal. So if you have coal and analyze, doing analysis, you are getting 30% carbon, then something going wrong. That's why you need to know what is the estimate. Okay, so now let's go to thermal power plant. What they do, they burn coal to get steam and electricity. And we are a smart guy say that mix some biomass and make green, less CO2, go green, maybe they will say hold on. Okay? You can burn biomass, but if you blend it together, you have a different carbon percentage. Alright? That is going to change boiler characteristics, that is going to change the flame length and other things. So they will say hold on, we need to design or something like that change. The other thing will happen, how do you feed coal to boiler? You have a conveyor belt, it goes to boiler. How do you feed biomass to boiler? Can you transfer sawdust like coal pneumatically? What will happen? It will transfer, then suddenly it will breach. Right? We have to set it up, then flow, then breach. So that's characteristic is different. That's why saying blend 30% easy, engineering wise it's not easy. Okay, you cannot do it. So then you can make char or pellets and then you can blend it. So any biomass or organic waste or organic matter, you want to know approximate analysis and net analysis. Why you need to know? Because you can write this formula and then you can do material balance. Now here if this was one store for me is how much fixed carbon and how much volatiles. One over fixed gas is only how much carbon? 43%, 44%, 57%. You won't say 60%. Alright? So this is the carbon value you are paying for making oil or anything crude or from this. Oxygen, lot of oxygen you will see. Nitrogen, not much, but if it's a protein compound, you will see some. Now this is our biomass or what is our ultimate objective? Making petrol, gasoline or jet fuel. Put crude oil next to it or coal next to it, how that will look like. Then we will appreciate the challenges of making. If you make crude oil, how this carbon will look like? Tell me a range. How much carbon in crude oil or gasoline? Definitely double than that, am I right? It's hydrocarbon. Right? It's close to 80-90% in that range. Double than that. So if you have this is more, double than that, this will go down. Right? It's simple math. If you have 80% carbon, this will be 10%, 8% and all. So I am simplifying for you. This is biomass and you want to make it oil, what you need to do? Can you tell me? Now, this is biomass and then I put the oil and I said 80-90% carbon we have to go. So what we need to do? Increase carbon content, reduce this. That's the chemistry we have to do. Thermochemically or biochemically, whatever. Very basic level. And oil, how it looks? hydrogen to carbon ratio from yesterday. What is the H by C ratio of oil? Gasoline, diesel, or all those things. Pardon? 0.2? So methane was how much was it? Hydrogen to carbon ratio 4:1 CH4. Hydrocarbon, how much is the ratio? 2:1, correct? CH2. Now you want to make this oil, and I should have put another table for oil, then it will be easier. But imagine now, carbon need to go 80-90%, hydrogen need to go H by C ratio 2. Okay? So what we have to do? So let me take a step back. If you want to do material balance, you need some formula, chemical formula, how to represent, then you can do material balance. So once you have elemental analysis or ultimate analysis, you can write this formula. Biomass, once you have done that, you can represent like this: C, H1.5, O.7, and it's not matching. But you do carbon, change in mole, you can write C4H6, something like that, or you make this one, so H1.5. So basically it's mole, you change in the mole percentage, and you can simplify this one, then this will look like this. What is H by C ratio here? This is biomass or organic waste particle. What is H by C ratio here? 1.5. If you want to make oil, what is the H by C ratio? 2:1. So from 1.5 to 2, you want to go. What you need to do? Math, nothing else. I'm not talking chemistry. Forget this. You want to make this 2. Either you reduce this or increase this. Am I right? And once you have started removing this, this will improve. Alright? So no matter what you do, you don't want to lose this carbon. It's a hydrocarbon business. You don't want to lose carbon from CO2. If you are doing thermochemical, you want to lose it, this will become CO2. And CO2 has no value, oxidize, no fuel value. So you want to protect this and you want to increase this, and you don't want these things. That's simple how we will do. You need hydrogen to add. That means you have to do some hydrogenation process. This is hydrogen deficient compound. So you have to do hydrogenation, and what else you have to do? You have to remove this. If you add, this will reduce, but you have to remove this oxygen. This is, in math it is 40%, 30%. So you have to do deoxygenation. You have to remove oxygen, you have to add hydrogen. Then only you can go to CH2 on off, dropping here. That's very fundamental. Much more added in that, the catalyst, temperature, water temperature, hydrogenation and other thing. But the thing is, this is hydrogen deficient compound, oxygen rich compound. You have to reduce oxygen, you have to increase hydrogen. That's why you need hydrogen. But this hydrogen can come from green hydrogen, electrolysis, so you can be innovative on that. But this is what needs to be done, and that's why we are looking from very fundamental. Now, if you are designing thermochemical process, pyrolysis, you will understand better. If you are looking gasification, you will understand better. Okay, what needs to be done? Let's say you want to turn this coal, not oil. You want coal, green coal. Because sometimes you want coal, sometimes you want oil. Right? So what needs to be done to get coal from biomass? Char. If you want to increase char, just you are worried about char making not oil or oil. What you need to do here? Put a table for coal. How coal will look, carbon percentage for coal. percentage of carbon you exchange in coal. Very high, right? 90%. More carbon, better to coal. And ash, sometimes you get so low quality coal, it will have more ash, high quality coal, it will have less ash, so that's why we import some coal we have, we do mixing or something like that. So coal quality matters, but you want carbon in coal, alright? Not much oxygen you want in coal. You won't see oxygen. How about hydrogen? 4:1 is gas, 2:1 is oil, right? Gas, liquid, now solid. What is the H/C ratio of coal? I showed you lignin there, it's a kind of coal. What is the H/C ratio of coal? Again, these are very generalized things I am talking. So H/C ratio of coal is close to what? CH bond you will see. Saw the lignin and look very closely, you will see CH bond more. So now to make this one, we need to increase carbon more, right? That's why we do carbonize. When we carbonize, we try to retain carbon in the solid form. That turns into H/C. So you don't need hydrogen here. And you want to remove oxygen, and oxygen when you want to remove it from here, both oil or coal case. Have you seen oxygen? If you heat something, do you see pure oxygen will come out? You have food and you are eating, and purpose is carbonization, that means you want to remove oxygen. So how oxygen will come out? There is no magic that I will solve and tell you. So you will heat it, gas will come. So oxygen will come as a compound, right? Not pure oxygen. It will come like a carbon dioxide or carbon monoxide or methane depending on what, or water, H2O. If you are making coal or oil, you want to remove oxygen, but your treasure is carbon and hydrogen gas. So in the process of removing oxygen, you will end up losing some carbon in form of CO2, and CO2 has low value. But that's the compromise you have to do. The process you will design there, CO2 is less, carbon monoxide is more, methane is more, because those gases have value, CO2 has not. Okay? So that's called decarboxylation or deoxidation. So if you are getting water out, that's fantastic, then you are not losing carbon, but you are losing hydrogen. So this example, if you see that, they are asking how to do representative formula, how to write that formula. This is just example for you. So you can see HN, sulfur, nitrogen are always less than 1% dose. You can neglect it, it's not very significant. So you can assume rest is moisture or ash or oxygen. So you can write ash-free basis this formula is giving 100 all CHNO as 100 and O you will get by difference 100 minus Cd minus H. And then you can do that and then you can write the formula HON. So you got O based on difference, then into mole. Then this to 1, so divide everything by 4.19, get 1, and this is the formula. We took a straw pyrolysis process, and pyrolysis process what you want to make, either char or oil. Let's say you make oil, and we did elemental analysis of oil. Okay? Carbon percentage is higher, that's the purpose you made oil. Carbon percentage goes low, that's not done. So now you look at it. Formula will change. You will see higher free, but this is not true. This because of these numbers. So once you get it, it's not yet there. So you have to hydrogenate, remove this, and now I simplify it. But H/C is 2, you have to go, and then these things should not be there. Okay, so that's why this bio oil is not very good oil. Because that formula looks like this. We think we made pyrolysis oil as a food oil. That need further upgradation to hydrogenation or deoxidation process to get this out, get this ratio right. So when we make pyrolysis oil, you will see a lot of water in it also. It takes a bit. And then you have to take it. So you can use this for heating purpose, low value, you can, this is oil, so you can burn it. Okay, but if you are giving to refinery and then diesel and petrol, is not ready. They will not take it. It won't blend with crude oil. So the idea of working on pyrolysis, you want to make it stable. This is not stable. It will change over time. So the stability will come removing this, taking more balanced oil. So fuel business is a steady energy content. Now look at here on this table and tell me what to see. Keep up, top to down. Uranium is highest because of it's a nuclear fission, that's a very different topic. Okay? Up to here it's all combustion topic. You get energy from conversion. And we want to make fuel. What we want to make is this gasoline, right? Diesel. We have to come to 44. Where we are? Gas. 15, 16, those things. Right? So again, same thing. If you look at differently, here, you have to come here, that means you have to do what? Do thermochemical process or biochemical process, you have to come out like that. Okay, so lower the oxygen content, higher the heating value that you want to remember. Now the thing which I was talking yesterday, many people don't like ethanol for different reasons. The one reason is heating value 30 versus 44. If you mix 44 and 30, definitely average will come down 35, 36. That means that much sacrifice you want to do. If you need 1 liter petrol, now you will need 1.2 liter petrol for driving the same distance. Okay? If I talk like this, then they will say no, it's not that simple. Now this ethanol is renewable. Okay? 5 to 10% ethanol helps in burning. Okay? You don't have this any oxygen here. It's a soup formation. So typically NA or something we added blend to gasoline blend or something we do that. Additive we added for clean burning. Now you don't need that additive, ethanol does that. Because of it brings some oxygen. So it helps clean burning, less soup formation. Okay, so we compromise that, but combustion is better. Now if you start increasing this percentage, this number average will still coming down. So how much you can blame? That's why I'm saying ethanol is a transition route. Everyone is looking for dropping. I don't want to reduce this. Can you make these things right here, not here? And that's the future, that's the drop-in fuel or fungible fuel. So you will see many projects, they are taking ethanol or making thermochemically catalytic method, right now. Okay. But if you are doing that, you are adding cost to it, so how efficient you can do, how good catalyst and all that such topic. But that's the thing, and someone is telling ethanol is not good, this is the way you have to explain. That's good. Certain percentage or probably this is renewable, which has a much better value environmentally. But that's why it's a blend. We don't go 100%. If we go 100%, how much compromise we will do in 5 years? Right? And plus, this is oxygen. And oxygen is the active compound. If you swell your prostate and other things, ethanol loves water. diesel does not require water, right? So ethanol, you will see another challenge. How we transport petrol or crude oil. Why? You can complete. Second thing is light water. It's beer vessels can dissolve and can. So if you are pumping, moisture will play a role. Pipeline over the time, water will seep, so moisture and also that will deteriorate the quality. So that's another challenge of ethanol. Plus another challenge of moving towards cropping. Tanker supply will not address country level demand here, alright? We need transportation, piping and all. So again, that's why we are moving away from ethanol for a drop-in fuel in future. That's the way. But I'm not no way saying that ethanol is not. Blend is always fine. Look at hydrogen and natural gas. Natural gas is 54, pure hydrogen. So now you will say, why don't we have hydrogen car? Green hydrogen car. You might have seen fuel cell, hydrogen cars, and other things, and then some things are slowed down, some things are picked up. So hydrogen car is mainly someone is looking at this number. So you need less of hydrogen to drive same amount. Okay? Then gas you can compress. So high pressure you can do, and it's clean burn. So it becomes water, so there is no pollution. That's why we are looking at hydrogen. The challenge is light gas. So you have to compress. Enough hydrogen in this room, you don't much. Unless you compress it, you don't get that. So you need high pressure tanks for vehicles. It's like a high pressure container you are running. The second challenge is, how do you get hydrogen? Oil to drill and then refine it. How do you get hydrogen? You have to split something. Hydrogen is not freely go mine or drill or something. You don't get it. It's not free of rock. It's always a carrier. Fuel cell works on hydrogen. Fuel cell is good efficiency. But how do you supply hydrogen to fuel cell? You need a fuel to make hydrogen. Okay, so if fuel cell clean, you are shifting how you get hydrogen. So hydrogen is very good fuel, but it's a carrier, energy carrier. You don't get free. Natural gas is a fuel because it occurs. It's naturally occurs, not hydrogen free. Okay. Then H/C ratio, which I already talked all these things. Atomic ratio Y is important, I just now talked. So this is one plot typically we do for biomass, coal or energy. So this is called Rank diagram. If you are publishing something, you have done some analysis in your manuscript, you want to plot Rank diagram. Look at that angle. How H/C ratio versus O/C ratio looks like. O/C versus H/C. It has a lineage from coal industry, but this is common way to represent your results and we can start discussions where we are. So biomass is here, H/C versus O/C ratio. And you can plot it because we did our ultimate analysis from there, we can do H/C and H/C you will see in this range. Okay? If you are looking for solid fuel, you have to come this way because anthracite best quality coal is here. All carbon, very low oxygen, very low. So now you did something and you want to look fair here, and maybe beginning will look like this. Okay, I need to go this far, what you are making. So Venn parallel diagram, it should be a good way for data representation or data analysis and other things. Heating value, I keep asking, how do you calculate? Forgot to mention, how you do heating value? No, I give you a figure for biomass and I ask you heating health, tell me what is heating health, how do you get it? We know wood has 50 to 16 values, okay, how we get that? In lab, how we measure heating health? Because we are talking same thing, 44, 42, hydrogen L1, 42, but how do we measure that? Have you heard about bomb calorimeter? So this calorimeter is burns in presence of oxygen and is calculated by heating value. Okay? If you don't have bomb calorimeter, we have done ultimate analysis, yes and OS. There are empirical formulas that confirm these numbers and its validity. That's the estimation. You don't have to have calorimeter all the time. You have done ultimate analysis, you can estimate heating value. There are many empirical formulas available. One of those is called Gibbons formula, which tells how much carbon, how much hydrogen, log everything, and you get some number that is heating value. Heating value are two types, high heating value, lower heating value, and yeah. H/C ratio, large biomass, expression linear, how is bomb calorimeter. Okay. If you don't have, still you can use CHNS method and you log formula. Heating value are two types, more on reading material, I don't want to go there, it take time. So Euler formula, one of the form looks like this. These are not universal formulas. These formulas are for biomass, wood, grass, different coal. So you will have to look at right empirical formula which fits in your range. And then we have done ultimate analysis. You can put those numbers and you will get high reading there. So it's another way to look at what you made in char. What is the heating value of char if you are looking at a solid fuel. If you are looking for land application, that's a different. If you are looking for solid fuel, you need to look at heating value. Moisture, how you report, because all these things has to be traded in market. How much price you want to pay. So someone will say 200 rupees per kg or ton as received. Take it from here, give it 200 rupees. Now you need to know how much you are taking. Is it 40% moisture or 10% moisture? What price I am paying for that? So that is as received pricing. Air dried pricing. If you do something air dry, how dry you can go? Can you remove entire moisture? What percentage flow you can count? If you air dry some food item or something, you think all moisture from? No, some moisture will remain. You can have a good number how much air dry you have, 2%, 3%, 5%. So that's the pricing for air dried price is 1000 rupees per kg. Do you know how much price I am paying for water? Dry basis, all moisture removed in a laboratory analysis you did right there and you say this is the moisture. Dry basis you can give price that will be reached for. Now ash free basis, ash is another thing, it's not going to give you fuel. So are you buying grass or are you buying some wood? Ash is different. One is 10%, another is 2%. So you want to base your pricing on ash free basis. But other is inert material you are not. So this is how it's reported. What are the things in ash, aluminum, iron, calcium and other things, so all in again. Bulk density. You see this? That's how bulk density matters. Denser material or less dense material. One truckload of pelletized or as it is material will be different. You want to know bulk density, how it's being transported. So how we measure it's easy. So we go through that. Food density, average density, biomass growth density, I'm not going to these things. Thermal conductivity, if you are doing some insulation material and other things, thermal conductivity is important. A specific heat, thermal processes. I have given one example, we have assumed the formula of biomass, you will see that, and it will ask heat of formation and other things. So it's not relevant. Okay, this one is not relevant. How will you do mass balance? Let's say this is the truck and this is the plant. Truck comes and solid fuel out. Green for here. This is the black box. Right? Here we are doing some L06 or something. So I bring 1 ton here, biomass, and you are getting only 200 kg of coal. What happens to it? You have to design the plant, this plant. Where this 800 kg goes, if you have 1000 kg and you get only 300 kg, what happens to 1 plus 700 kg? Here they go. It's like our money. If I earn this much, 1000 rupees today, and tomorrow I have only 100 rupees. There 900 gone. You need to know. That's mass balance. Based on that, you design pipeline because this is going this way, so this needs 5 inch diameter and all those engineering details. So mass balance is the key to any conversion process. Key for everything. In and out you need to know. Okay? In everything. So if you want to do mass balance, this is the box what I showed. This can be a plant, this can be a fermenter, this can be a pyrolyzer, this can be whatever you say, oven or anything. What are the things coming in and what are the things out? Let's say this is a boiler. And you are running boiler on coal or natural gas. Let's say natural gas. So natural gas pipeline coming here and maybe air you are supplying. Let's forget this one. You need only those 2 things in this case. What is coming out? CO2. Because this is boiler, you are burning natural gas. What is coming out? CO2 and water. Alright, if you have air, then nitrogen. Oxygen getting consumed. How will you do material balance in this case? Material balance means what comes out, what goes out. Comes in, what goes out. So methane can, methane does not go out. So how will you do material balance? You are trying to track something, but that compound will change now. So how will you do material balance? It's very simple concept, but you have to figure it out. Simple accounting, atom economy. So since compounds are not stable, you go to atom level. Since CH4 is coming, no more CH4, but C is coming. C will be here in CO2 or carbon monoxide. So let's do atomic balance. How much carbon it came, how much carbon gone in CO2 atom. Now you can do material balance. Right? So that's why ultimate analysis you need. If you don't know carbon percentage, you can't do material balance. So once you understood that, it's very simple. Input minus output is accumulation. Alright? I put some this way, something came out, it is not equal, and then it's here. Alright? It's accumulated. So input minus output, accumulation, and mass rate is speaking with time and other things. At a steady state, accumulation is constant. This can fill only this much. After that, it's overflow. Right? Initially, we started, it's filled up to this level. Accumulation now is coming out. So accumulation constant at the steady state, you can say 0. in equal to out. 5 kg per hour coming should be 5 kg per hour out. Maybe different compounds. So this is one example. The chemical changes due to chemical reaction due to combustion process. So natural gas boiler is methane, air. Air is oxygen source, but you have nitrogen also. You get CO2 and water. Now you have to get control volume and do material balance. Because if you don't know how to do that, how will you design pipeline for how much water vapor will come out? Engineering part of it. How much water will be generated, then water pipeline condensation will need to be done. CO2, how much CO2 will come out, so you have to design flow rate. So this one example I will go quickly and you try to see is in the slides. So we have 1 kilogram of methane reacts with air. Okay, it can be oxygen also, but yesterday I was talking oxy-fuel versus normal combustion. So oxygen has cost, so many boilers run on air. So air, all the methane is to be consumed. You assume that 100% methane combustion. Maybe 99%, 99.5%, but let's say 200. How many kilograms of carbon dioxide, water and nitrogen will appear in the product stream? Because nitrogen will not take part in combustion. Few will be oxides, but mostly nitrogen. So, if you don't know how will you design? It's a boiler, then you have to design pipeline tanks and other things. Right? So, you know this one, CH4 plus O2, CO2, water and nitrogen. But we don't know, we know 1 kg, right? So 1/16 moles, right? This much coming, we know. We need oxygen, but oxygen comes with nitrogen. Here we can represent O2 plus 0.79% of ratio of nitrogen versus oxygen. So you can write this air formula and A, we don't know how much air we need. Right? Then CO2 will come out, we don't know how much, that need to be calculated. X. Water will come out, we don't know how much, Y. And nitrogen, G, we don't know. Now you do material balance. What is carbon balance? How much carbon? 1/16. No carbon here, no carbon here. X carbon here. X equal to 1/16. So you can get how much CO2 came out. This is the simplest one. Once you know carbon turns to CO2, CO2 44 divided by 12 CO2. Right? It's very simplest one. But now you know X. Start from there, go to hydrogen balance. This is the formula. How much hydrogen? 1/16, 4 equal to 2Y. You solve it, Y equal to 1/8, you move one step ahead, now you know how much water. Because of atom balance, atom. Now you go closer, oxygen, do the same thing. Now you know X and Y both, so you can use that formula, you will get A equal to 1/8 moles, so 4 kg of oxygen. Go to nitrogen, 1/1, simple question for the solution to the problem. Nitrogen will get 1.7 mole. Done everything. You should practice in any lab experimental analysis in and out. Control volume. That will clear your thoughts, what was coming in, what was going out. Okay. That will tell you how much conversion happened, percentage conversion. This is methane and corn. There will be sugar and ethanol. You can balance it out. Percentage conversion of sugar to ethanol. You have ethanol this is, you have written the equation, you know equation. Put it like that in dots and it's very, very clear picture will give you. And if you are not getting in equal to out, then it's sitting in your reactor or some mistake happening. That's it. So this is the way we should look for all this mass balance. This is very fundamental. should look that very closely. Then you start, now I got a good result. It can be exciting, but when you do this, it's not something normal. So cross-check with material balance. The next one is energy balance, which many a time not required, but energy balance is same math, input minus output equal to accumulation, or if there is any generation, it's okay, cannot, then 0 in equal to out. Here you do enthalpy balance. Your kg becomes heat. Kilogram no, more heat now, joules and all. So you do the same thing, control column and all. Not very much required for you at this stage, but the first one is, this can be fermentation, this can be pyrolyzer, this can be gasifier, anything. Carbon conversion, you want to know how much carbon in methane, how much carbon. This is not useful, this is useful. So you have to see that. There may be another product with charcoal here, then you will know how much carbon you want to charcoal, what is the percentage conversion carbon into charcoal. So with that, how are we doing a time, Bhavan?
15 minutes.
Another 15 minutes?
Yes, sir.